All right, this is Mr. Willis, and we are continuing on with our learning. Um, let's see, you guys are doing great. You've been doing so well, and now we are continuing doing some learning and some notes here. We just finished talking about the fact that a barometer is used to measure atmospheric pressure, and then we wrote in some of our units that are all equivalent to 1 atmosphere and are thus equivalent to each other. And now we're going to do just some conversions, just a little bit of practice using some skills that we have before, but never hurts to dust those off and use them again. All right, remember the first step is always going to be to write down what we're given. So I'm going to write down 1.50 atmospheres. And I'm going to go ahead and write my units in there. Now, I want to get rid of atmospheres and I want to get to millimeters of mercury. So since I want to eliminate atmospheres, I'm going to write that down here on the bottom. And I have that 1 atmosphere is equal to 760 millimeters of mercury. So I'll write that down right here. All right. Now when I multiply that across, I'll take 1.5 and multiply by 760, and that will give me my answer. Everyone go ahead and punch those numbers on your calculator, and I'll do the same. 1.5 times 760. All right, and I got 1,140 millimeters of mercury. You always need your units, and we know that those are the units that are left because atmospheres reduced away since it was on the top and the bottom. And that's what we wanted to happen. All right, now what if we want to convert millimeters of mercury back to atmospheres? Well, let's start by writing down what we're given, 190 millimeters of mercury. And I'm going to go ahead and put millimeters of mercury on the bottom, and I'm going to be converting to atmospheres, so I'll put atmospheres on the top. Now, and again, 760 millimeters of mercury, so I'll just fill in that number there, is equal to 1 atmosphere. Fill that in. All right, and so this time I'll take 190 and divide by 760, and I'll let you do that, and just by my rough math, that'll be around 0.25. All right, so let's clear the board there, and let's move back to our discussions in our PowerPoint. All right. Okay. So we took a look at those. All right. So units of pressure, and there we have it all written out in the form that we filled in our notes. All right, and here we have exactly what we did on the other page. And so again, we've confirmed 1,140. Let's see if they show us the next one and give us the answer to that one. Sure enough, hey, and look at there, 0.25, so my math was not as rough as I thought it might be. All right, so we've got those. All right, the pressure at the top of Mount Everest, the tallest mountain in the world, is 253 millimeters of mercury. Remember, as we go up, the atmosphere becomes less dense, and so there's less atmospheric pressure expressed in atmospheres. So we would like to just forget that you've seen this. Just don't even look at that. Again, the way that we would work that, see if you can work that and come up with 0.33 atmospheres just by working that on your paper. What's the first thing you would do? Okay, hopefully you said write down what we're given, and so that's going to be 253 millimeters of mercury. And since we want to get out of millimeters of mercury, we're going to put that on the bottom so that those will divide away. And we'd like to convert to atmospheres. And if I look back on my notes, what numbers are going to go in there? that 1 atmosphere is equal to 760 millimeters of mercury. And again, you must have equivalent values over each other in order for this to work properly. So 1 atmosphere over 760 millimeters of mercury, do the division, and hopefully you'll come up with 0.33. All right. All right, so let's see what is new for us in the kinetic theory. We talked about this, the kinetic molecular theory of gases, on our last slide. Let's see. All particles are in constant motion. Again, we remember that the gases are always moving, that it is mostly empty space, that the particles move in a random and continuous motion in a straight line until they strike something and then they collide and bounce, and that those collisions are elastic, meaning that energy is completely conserved. All right, let's talk about standard temperature and pressure. Remember that if you increase the temperature, you increase the molecular motion, and thus you would also increase the pressure. Also, if you change the volume, you would change the pressure. And we're going to talk about those relationships on another day. We are not going to talk about those today. So, just like in math, you have standard form for some equations. In chemistry, we have standard conditions, standard temperature and pressure. And it turns out that the standard temperature is 0 degrees Celsius, and standard pressure is 1 atmosphere. Go ahead and write those in your notes. That I saw that was going to be one of our next conditions. So standard temperature 0 degrees Celsius, standard pressure 1 atmosphere. All right. Now, and also just record there in the margin, wherever you can find some space to, that 1 mole of any gas at STP, which is standard temperature and pressure, 1 mole of any gas takes up 22.4 liters. And so that is just like in particles, we said that if there was 1 mole of a solid or liquid, that contained 6.02 times 10 to the 23rd molecules. For a gas, 1 mole of gas takes up 22.4 liters of volume. Right? Okay. Dalton's law of partial pressure. So there's a gentleman named Dalton, last name Dalton, who I believe his first name may have been Charles, but I'm not sure. Oh no, I'm probably making that up. You can Google it and find out what Dalton's first name was. So, and he identified the truth of the universe, that if you have a mixture of gases, the pressure of that mixture is equal to the pressure of all the combined partial pressures, or all the combined parts. So the pressure of a mixture of gases is equal to the sum of the pressures of all the constituent gases, meaning the gases that make up the mixture. And so sure enough, if we have 1 atmosphere, if we have some oxygen that's under 1 atmosphere of pressure, some nitrogen that's under a half atmosphere of pressure, and some hydrogen that's under 3 atmospheres of pressure, and we combine those all in the same volume container, remember changing the volume would change the pressure, but if we combine those all in the same volume container, then the total pressure would just be the sum of all of those added up, and that would be 1 plus 0.5 plus 3, and that totals up to 4.5 atmospheres. So Dalton's law is fairly straightforward. It just tells you that your total is equal to the sum of your parts. All right. So the total pressure is equal to pressure 1 plus pressure 2 plus pressure 3 plus however many pressures there are. All right. And then that will give you your total. So let's work a sample. if we have a mixture of neon and argon that exerts a total pressure, okay, so let's just look at what we have here. Total pressure of 2.39 atmospheres, and the partial pressure of neon is 1.84. What is the partial pressure of argon? Okay, remember that our total pressure is going to, in this case, equal the pressure of neon plus the pressure of argon. Now our total pressure was 2.39. We're looking for the partial pressure of neon, and the partial pressure of argon was 1.84. And so it's easy to see that if we take 2.39 and subtract 1.84, that will leave us with just the pressure of neon. Let's see, 9 minus 4 is 5. Did you know you could do this without a calculator? It's cool. 13 minus 8, oops. 13 minus 8 is 5, I think. And then my 1's subtract away. And so that is then the partial pressure of neon, 0.55 atmospheres. All right. There we go. Let's see if they were kind enough to tell us the answer if we click again. If we click again with our mouse. Oh, nope. So, oh yeah, sure enough, 0.55. Great. Okay, so what is the total pressure of a mixture of gases that's made up of carbon dioxide, oxygen, and hydrogen if the partial pressures are this many kilopascals, and this many respectively? Respectively just means that the pressures are listed in the same order that the gases were. So carbon dioxide is 22.3, oxygen is 44.7, and hydrogen is 112 kilopascals each. All right, well, to get our total, all we'll have to do is just add those up. And so P total will equal the partial pressure of CO2 plus the partial pressure of oxygen plus the partial pressure of hydrogen. Okay, and just take a moment, pause, and add those up, and see what you come up with. All right, and I have come up with 179 atmospheres. Oops, excuse me, it's not atmospheres, it's kilopascals. 179 atmospheres would be an incredible amount of pressure. You would not be doing well with that amount of pressure. I'm thinking of a David Bowie song that you can also Google on the internet. All right, so Google David Bowie and pressure and see what comes up. All right, let's, and it should be a song called Under Pressure. If anything else crazy comes up, I'm not responsible. So let's move on then. Sure enough, 179 kilopascals. All right, and our last topic for today, I know that you are thrilled, proud, happy, and thrilled to hear that. Last topic of the day will be Graham's law of effusion. And you're like, Mr. Willis, did you misspell diffusion? No, I did not. It is effusion, and that is slightly different. Diffusion is when molecules move from an area of high concentration to lower concentration. And this happens all the time. If you light a candle, if you spray some perfume on something, and then it gradually diffuses out and you can smell it across the room, that is diffusion. Effusion is the rate of diffusion through a small opening. So diffusion is just open movement of those gases and molecules, and effusion is specifically the movement through a small opening. All right. Now, interestingly enough, okay, so we're gonna hit some heavy math here, and I'll just show you what it looks like in a minute. The rate of diffusion, or effusion, is inversely proportional to the square root of its formula mass. What? Okay, here's what that means. Lighter gases effuse faster than heavier gases. And I'm sure that you don't need a chemistry degree to think, hey, if I have lighter molecules, they will diffuse or effuse faster than heavier gases. That actually is a little weird, though, to think that if you have a lighter gas, then it might move out of a closed container through a small opening faster than a heavier gas. However, I intend to show you. Here's the mathematics of that. That the rate at which A effuses and the rate at which B effuses, that the ratio of those is equal to the square root of the molar mass of B divided by the molar mass of A. So there's Graham's law, and I'm sure that there is a lovely spot for you to add that. Oh, it's actually already added in your notes, so you do not have to add that. We will go back and fill in those notes in just a moment. All right, so again, lighter gases effuse faster than heavier gases. Mr. Willis, I'm not sure. Okay, so two gases of different mass would move through the same size opening at different rates? Absolutely. Mr. Willis, I don't know if I believe you about this. Don't believe it? Let's check it out. And this is when we contact the server. And, okay, here we go. They're two identical balloons, but two different gases. One with helium and one with Professor Brett. That's code for just air. Alright, and here's what should happen. The lighter gas should effuse faster than the heavier gas. And you can see that the balloons actually deflate at different rates, which is crazy. And to me, that is just absolutely bananas that you would have two balloons, same size, same type, same filled with the same size and amount of gas, but that the helium would empty out faster through the same size opening. But that is what Graham's law tells us, that the lighter or gas with less mass, less molar mass, will effuse faster. And you have seen it with your own eyes. All right, let's finish filling in our notes for today, and I think that will do it. We'll double check. Okay, we'll do a quick, which gas would effuse the fastest, nitrogen or chlorine? Well, N2 versus Cl2, nitrogen has a smaller mass, and so it will effuse faster because it is 28 grams and chlorine is 70 grams. So nitrogen will absolutely be effusing fastest. And we saw a demonstration of that as well. All right, so let's go back and finish filling in our notes, and then we will be done for the day. And oh, actually, I have some practice for you. Sorry, shouldn't tease you like that. All right, Dalton's law of partial pressure. Pressure of a mixture of gases is equal to the pressure of the constituents of all, is equal to the sum of the pressures of all the gases. Okay, so now we've figured this out. Is equal to the sum of the pressures of all the gases. And there's our P total equals the sum of the P parts. Graham's law of effusion. Diffusion is the spreading out of particles. And the rate of diffusion of gas is effusion. Again, typically, I just want you to write over to the side, typically through a small opening. And it is proportional to the inverse root of its formula mass. And the real take-home message is that lighter gases effuse faster than heavier gases. That's what we were really concerned about. Okay? Now, at this point, you should have So at this point, you should have a couple of practice pages. Let's see if I can find my copy. Page 160-4 and page 160-8. One for Graham's law of diffusion and effusion, and one for the Dalton's law of partial pressures. Okay, so let's look and talk about how we would work number 1 and maybe number 2 of Dalton's law of partial pressures. So the first says a sample of gas containing partial pressure of carbon dioxide, and let's just pause for a minute. And so the pressure of carbon dioxide is going to be, let's see, it says it's 0.72 atmospheres. That the pressure of oxygen is 0.76 atmospheres. And that the pressure of nitrogen is 0.42 atmospheres. And it says what is the total pressure of the gases if these were all contained in one container. All right, remember that P total is going to equal the partial pressures of all of these. So PCO2 plus, that's a 2, plus the pressure of O2 plus the pressure of N2. All right, so take a moment. Let's fill those in and work the problem and see what we get. 0.72 plus 0.76 plus 0.42. Ooh, it's an ugly looking 2. And the total pressure then will be the sum of all of those. And of course, since those were all in atmospheres, the correct unit for this will be atmospheres. And I'm not going to solve it for you. I'm going to let you punch the buttons, but it should be the sum of these 3. And I think that you're very capable of taking care of that. All right, so let's clear the board and look at a second one. All right. If nitrogen has a pressure of 460 torr, what is the pressure of the oxygen? Oh, well, we don't actually need any of that information about torr and about the nitrogen. We can just look and say, hey, the oxygen is 0.76 atmospheres. 0.76 atmospheres. And I'm going to convert that into torr. So I'm going to put 1 atmosphere down here. I'm going to look back up in my sheet and see that 1 atmosphere is equal to how many torr? I think 760. Okay, and so then once again, I will take 0.76 multiplied by 760. My atmospheres will reduce away, and I will be left with my pressure in. And that was the pressure of oxygen, I believe, yes. And that will be my pressure in torr. Okay? So at this point, I would like you to go ahead and complete the odd. So complete 3, 5, 7, and 9. And then also complete your Graham's law of effusion on the back. All right? So continue to work on that for the remainder of the period. Thanks very much. Have a great day.